All right, so our post-AP lesson number 4 is on integration by parts. So basically when you go on in calculus, so if you go to Calc 2, Calc 3, and so on, you're going to need to be able to look at an integral and say, oh, this is a chain rule problem. Dang it, I was right the first time. A U substitution problem. Or this is a integration by parts or partial fractions. So we have to learn all these different methods to integrate. Okay, so the one we're doing today is integration by parts. So do you guys know how U substitution is the opposite of the chain rule? This is the opposite of the product rule. Okay, so the proof of this is kind of a little bit confusing.
Ew.
I'm going to show you a quick little piece of it. So it says the derivative of f of x times g of x, that's the product rule. So it's going to be is f prime of x times g of x added to f of x times g prime of x. We all know that. So it says, therefore, if we integrate both sides, we end up getting f of x times g of x, because we're integrating this part, and we'll really kind of bring that integral sign in, equals the integral of f prime of x g of x added to the integral of f of x g prime of x. And if I want to get this part by itself, so the part right here I'm circling in blue, if I want to get that by itself, I'm going to take this one and subtract it over. So it's going to be our original functions f of x times g of x, and then minus the integral of f prime of x g of x. So we really never write it like that in textbooks. We always just use u and v's to replace those functions. So the easiest way to write it is that the integral of u dv is equal to uv times the integral of v du. Okay. I personally don't even memorize that because I had trouble with it when I was in calculus, remembering which one was the v and which one was the u. So I just do a little method, okay? And I'm going to show you the method that I do. So for example, if we have something that looks like this, x times cosine of x, we are not able to integrate this with any methods that we know. We can't do like a u substitution or anything like that. So we have to know this new method. So what we do is we define something to be u and something to be dv. So we're breaking it apart into pieces. The u is usually what vanishes. Now by vanishes, what I mean is if I had x cubed, when I take its derivative, it's 3x squared, then it's 6x, then it's 6, and then it goes to 0. That's what it means to vanish in math. Okay, it means as you continue to take the derivative, it goes to 0. So what part, the x or the cosine of x, vanishes? The x. So almost all of the time it's going to be the thing that vanishes. I'll show you the few times when it's not. So I do x, and then the rest of this, I have the x, but then I have the cosine of x dx. So I'm going to make the rest of it cosine of x dx. Okay? So for u, we're going to take the derivative of that. We're going to get what du is. So we're finding the derivative. So what's the derivative of x? 1, and we'll put the dx there. And for dv, we're going to integrate. So when we do that, sine of x, its derivative is cosine, right? Okay, so if you set it up like this every single time, there's a pattern. So look at our equation, it's uv. So where are uv? Here and here, right? And then it's v du. Well, where's v du? Here and here. So if you always do downwards diagonal minus bottom row, you'll be good to go. I didn't mean for that to rhyme, but that's pretty cool that I did make it rhyme.
Oh, that is cool.
All right, so our integral of x cosine of x dx ends up being the u times v, so x sine of x, minus the integral of that bottom row, so sine of x dx. Do we know how to integrate sine of x dx? Yeah, so the derivative of sine is cosine, so the integral is negative cosine. So I'm going to have minus a negative cosine, so plus cosine of x, and then we tack on the plus c at the end. That's our answer. Yes?
So the u is the one that like would eventually go to 0.
If you kept taking the derivative
the
over and
dv
over.
is like whatever else is
Yeah.
left.
Wait, how is it plus cosine of x?
Because the integral of sine is negative cosine. So if I do the antiderivative.
It is?
So the derivative of sine is cosine. So the antiderivative is negative sine. Or negative cosine. Negative derivative. All right, so this one. Yeah. So now we have the integral of natural log of x. So when we have natural log of x, how do we integrate that? That's the whole problem, right? We're trying to integrate natural log of x. We don't know how to take the integral of it, but we do know the derivative of natural log of x. Do we all know that? 1 over x. Okay, so that's going to be the part that you're going to set as u because we know how to take the derivative, du. So this is one that doesn't necessarily vanish. It doesn't go to 0 as we keep taking the derivative, but we know how to take the derivative of natural log of x. We know that we get 1 over x. So then dv is the part that's left. Well, if I let u be natural log of x, the only thing that's left is that dx, right? So like 1 dx, or just dx. So if I do the antiderivative of that, I'm back to x. Sorry, I always put the dx's with the d's. So du has a dx and dv has a dx. I sometimes leave them off, as you guys always do on your homework, so don't judge me. You don't get a bonus point when I leave off the dx's.
What about for people who don't leave off?
You
Well, that's
already
good.
got those points like years ago.
And she did get those points years ago, yes. All right, so we do uv. So uv is the downward diagonal. So we're going to do x natural log of x minus v du. So the integral of v du is going to be, well, it's going to be x times 1 over x dx. Well, how does that simplify? Yeah, it just becomes like 1 dx, right? Or just dx. So if I integrate dx, I get x. So if you've ever wondered, how do I find the antiderivative of natural log? We just did. The antiderivative of natural log is x natural log of x minus x. Make sense?
Redunculus.
All right. So clearly we need to know this method because that's how we're able to integrate things like that, right? So this next one, x times 2x dx. So we're going to let our u be the x. Our dv is going to be 2 to the x dx. So we take the derivative of the u. So u, it's u is equal to x, so its derivative is 1 dx. And then the antiderivative of 2 to the x. The antiderivative of 2 to the x dx. 2 to the x divided by natural log of 2, not multiplied. Its derivative is 2 to the x times natural log of 2. So remember, its antiderivative was divided. I know. Emily's like, derivatives and antiderivatives are the same problem. That's what's confusing about it. So we get 2 to the x over natural log of 2.
Why is it over natural? Like, is that just the rule?
That is the rule. So we had a rule for a to the x. But basically what happens is,
I remember that. Okay.
you remember that?
Yeah, I remember that.
Yeah, you have to undo that constant from the derivative. So if you took the derivative, you'd gain a natural log of 2. So we have to undo that constant.
I think I might sneeze.
All right, so here we go. So we do uv.
Okay.
So x times 2 to the x over natural log of 2 minus v du. So 2 to the x over natural log of 2 times dx. Okay. Natural log of 2, that's just a number. So what can we do with those numbers? Yeah, just kind of pull it to the front, right? So let's kind of simplify. So we have x times 2 to the x over natural log of 2. And we're going to have minus 1 over natural log of 2. And then we have the integral of 2 to the x dx. Didn't we just do that?
Oh, not necessary.
We have that, right? So we end up having x times 2 to the x over natural log of 2 minus 1 over natural log of 2 times 2 to the x over natural log of 2 plus c. You can leave it like that. So some people in the last class were saying, wait, shouldn't you have like a parenthesis so it's really going to be like c over natural log of 2? Why did I not care about that? C divided by natural log of 2 is still a constant, right? So if I just put a c on the end, I'm fine. So a lot of times on these problems, we'll just tack on the c at the very end of the problem. Yeah.
So it's uv minus.
Yep. The equation is uv minus v du in an integral. So one of my students a long time ago, one of the first years I taught calculus, took a picture of something and was like, why didn't you teach us this? and it was this formula, and I was like, I did. Like, I taught you that formula. I just never, like, revert back to the formula. I always just do the downwards and then the bottom. So it's up to you guys. You can always go to the formula. You like the formula?
That's why we love physics.
You just memorize formulas. All right, so use integration by parts twice. Oh, it's like a double chain, kind of. It's like you keep going and going and going. So this one we're going to do twice. So what do we think our u is, and what is our dv? X squared, and dv is the rest of it, sine of x dx. So du then is 2x dx, and v is, antiderivative of sine is negative cosine of x. You trying this? You writing this down? Did you lose your notes?
Yeah.
That's unfortunate.
No, they're at home. I just forget to bring them.
So negative x squared times cosine of x, and then minus, we have the 2x dx times negative cosine of x. So negative 2x cosine of x dx. So you can clean it up a little bit, like these two negatives and the two, right? There's lots of things you can do to kind of clean it up. So I'm going to write it as negative x squared cosine of x plus 2 times the integral of x cosine of x dx. And this is where you guys are like, why? Do you see? We do it again. So now we have this, and we need to do integration by parts.
Example 1.
So we're still doing it. Oh yeah, we did get the thing from example 1. Did I already do this? So we let u be x, and dv is cosine of x dx. And then du is then 1 dx, and v is sine of x. And to show that I did it twice, I will do little subscripts. You don't have to do this. I'm fine if you don't. But it shows, okay, this is the second time I've done a u substitution. There's something in Calc BC which is called the Tabular Method, and that's used when you have to go like 5 different times. It creates like a little table, and there's like a pattern to that table. All right, so here we go. So we have negative x squared cosine of x plus 2, and then we have the integration by parts, so our uv minus the integral of v du. So uv is going to be x sine of x minus the integral of v du is going to be sine of x dx. So we have negative x squared cosine of x plus 2x sine of x minus, I'm going to distribute the 2. What do I get when I integrate sine? Did I forget my x?
Oh, yeah, that'll be a point for 8.
Oh,
It's okay.
I'll give Evan it.
Yeah.
He raised his hand. He was waiting so patiently. All right, so what do I get when I integrate sine of x? Cosine, negative cosine, what do we think? Negative cosine, so I'm going to make that a plus, and then I'm going to do a cosine of x. And then at the very end, plus c. Done. It wasn't too painful. You guys got it. Now what do we think about number 5?
I think I'm done for the day.
It's torture. Why is this torture? I don't know. The last class was saying it was hard too. You guys got
We
this?
also checked out
Yes.
Susan and not here.
You know, seniors, senioritis. You guys had that from like August.
No, like seriously.
I know. This is not my first rodeo teaching seniors. Surprise, surprise.
Yeah.
All right, here we go. So, which one vanishes?
B.
Neither of them vanish. So you can let u and v be either one in a situation where you have like an e to something and a sine or cosine. So you can let it be either one. It doesn't matter. This one's my favorite. I love this. We do such a slick trick. It's so exciting. You excited? You look totally excited right now. All right, so we let u equal e to the 2x, and then we let our dv be sine of x dx. So when we do our du, we end up getting e to the 2x times 2 dx, and for v, we get negative cosine of x. So we started out and we're like, okay, we're good. We got negative, we got an e to the 2x, we got a cosine of x, that's our uv, minus the bottom row, the integral of the bottom row. So I'm going to pull out that negative. See how we have a negative and we have a 2. So I'm going to have plus 2 times the integral of e to the 2x cosine of x dx. It's never ending. Oh my gosh, it's never ending. Do you think that means we can't solve it?
Infinity.
No.
Yes, it's
We can,
Does not
because there's a trick. I just told you, a slick trick, right? So we get u equals, so we're going to go again. So we do e to the 2x, and du then is e to the 2x times 2 times dx. And our dv is cosine of x dx. So v is going to be sine of x. So then we do this part, right? It does.
What does the
So we're going to get negative e to the 2x cosine of x. It is not useless.
Get
You
it?
guys give up.
Useless.
You give up so quickly. You're just like, I'm done. I'm done with this.
I like things straight.
We are fine. We got this. So minus. So what are we subtracting? So we're subtracting that bottom row. So we have a 2. So I'm going to pull that 2 out. And then we have the e to the 2x sine of x dx. And this is where Ethan said, but it's just what we had originally. It is, totally. It's what we had originally. So here's our trick.
Where's Emmy?
We're going to let this equal w. So w is equal to all of this stuff, and the w was repeated here. So let me write this out so we can see it. So we have w is equal to negative e to the 2x cosine of x. I'm going to bring that 2 in as I go. So plus 2 e to the 2x sine of x minus, I'm going to distribute the 2 here as well, 4 times w. I agree. So how do we solve for w? Just like algebra, how do I get w's by themselves? Add the 4w over. So I get 5w equals negative e to the 2x cosine of x plus 2e to the 2x sine of x. So now we divide everything by 5, right, to get w by itself. So our final answer is w is equal to negative 1/5 e to the 2x cosine of x plus a 2/5 e to the 2x sine of x. Am I done?
Oh, we got
Plus
one.
c, thank you.
Plus C.
Plus c, of course. That's it. So when you see that you have the same thing that you had before, so same as original, you let that be w, and then you basically can get all the w's on one side and divide. It's rare that you have those ones. They're usually pretty easy. They're usually like the example 1, example 2. Okay, makes sense?
How far would you have to go? Like in this class, how many times would we have to do?
Twice.
Okay.
Is the most. Yeah, in Calc BC, that's where when you have that tabular method. So if you have to go like 5 times, 6 times, then you would do that. Okay, so the next one, number 6. Okay, so we could let our u be the thing that vanishes, in which case I would let it be like x cubed. But then we run into an issue. So if we let, so don't write this, if we let u be x cubed and dv is natural log of x, how do we get that v? Do we know what it is? We actually already found it in a previous example. But that seems even more complicated. It's not making it easier on us, is it? So when you have natural log, let that be your u. Because what's the derivative of natural log? 1 over x. And that's going to help us. So as I take the derivative of u, I get 1 over x dx. And as I integrate v, I get 1/4 x to the 4th.
Holy cow.
Okay. So there's some stuff that's happening here. So we're doing uv is going to be 1/4 x to the 4th times natural log of x minus v du, the integral of it. So I'm going to pull out that 1/4, and I'm going to have a 1 over x times x to the 4th dx. So this 1 over x times x to the 4th is going to simplify before I do the next step. Can you see what that is? So you can just cross it out and write the new one if you want. But so it's going to become x cubed. So what happens when I integrate x cubed? What do I get? 1/4 x to the fourth. So do you see how we have a second x to the fourth, or a second 1/4? 1/4 times 1/4. Do you guys see that? Okay. So we're going to get 1/4 x to the fourth natural log of x minus 1/4 times, the integral is 1/4 x to the fourth plus c. So you could pull out some common factors, like you could pull out a 1/4 x to the fourth, or you can just kind of combine those 1/4s. So I have 1/4 x to the fourth natural log of x minus 1/16 x to the fourth plus c. That's probably how I would write it. Mm-hmm. Oh, I had numbers, dang. All right. I had limits of integration, didn't I? So now you could just plug in the 1 and 2 from here if you messed up like I did and went all the way to the end. So you're like, oh, forget that plus c. I'm going to do those numbers. So I'm going to go from 1 to 2. So we'd have 1/4 times 16, right? 2 to the fourth, 16. So 16/4 is 4. Natural log of 2 minus 1/16 times 16. So I think it's just minus 1, right? So 4 natural log of 2. Oh, I'm not done yet. I still need to plug in the 1. I was thinking the whole 1 went away, but only part of it goes away. So minus, when I plug in 1, that natural log of 1 is 0. And then I still have that 1/16. So I think I get 4 natural log of 2, and then I have minus 1 plus 1/16. So I think it's minus 15/16. That's the answer. I think it's minus because it was negative 1 and then plus. All right, so the way that I typically write that when I have numbers in the problem, like I would have put 1 to 2, and then I would do 1 to 2 there. So as you go, you can kind of take care of that first part and then do the second part. Does that make sense? Do you guys see it? Okay, so number 7. So one disadvantage you guys have had with not having an actual calculus book that you go home and try problems in, like I made that an optional thing. How many of you guys actually got that? No one?
Wait, what?
Like got the book?
I have the book.
Okay, did you use it?
In the
No.
beginning of the
You
year.
can, so you can use it. It's a good book. It's my favorite calculus book. But you don't necessarily need it, and that's why I got an old edition. It cost you a whopping $4.
Whopping, but
So-
Mrs. Cox is buy
You
ice
didn't
cream.
even-
It's a good one to have if you do take like Calc 2 or anything. So in calculus books, though, there's like reference pages. So there's like reference like all the possible derivatives. So there's a whole bunch of derivatives on that page. There's a whole bunch of integrals. So there's like shortcuts to finding things. So there would be something in that calculus book that looks like this, and then there would be a general form for that.
Do you know if I can use that book next year if I'm taking the same class, or do I need to get a new one?
I would keep it, yeah.
But
It's used a lot. All right, so here we go. So if I'm doing this pattern, do you guys see how this is kind of like the last one? X cubed natural log of x. So if I have x to the n natural log of x, then we let our u be which one? Natural log. Because then we take the derivative and we get 1/x dx, and we let our dv be x to the n. So how do I integrate something that's in the form x to the n? So I get x to the n plus 1, 1/n plus 1. Definitely put that away. All right, so I get that. Forgot my dx up there. I told you I would do that. I do that all the time. And then we do our u, v. So I do 1/n plus 1, x to the n plus 1, times natural log of x, minus 1/x dx, times 1/n plus 1, x to the n plus 1. Okay, so I know there's a lot of symbols, a lot of variables. We got this. The n is some kind of number. N is a constant. Okay, so we're going to have still that 1/n plus 1, x to the n plus 1, times natural log of x. But there's parts that are numbers, right? This is a number. That was like our 1/4 from before. And we pull it to the front. So we're going to have 1/n plus 1. And then when we combine 1/x and x to the n plus 1, so I have x to the n plus 1 over x to the 1, basically. What do I get? I get x to the What power? N, because you subtract your powers. Just like if you had x to the 7th minus x to the, or divided by x to the 1st, you subtract your powers, right? So this becomes x to the n. So when I integrate x to the n, I get another 1 over n plus 1. That's why in that last example I had 1/4 twice. Do we see it? Because I integrated it in my UDV step, and I integrated it again. So my final answer is 1 over n plus 1, x to the n plus 1, times natural log of x, minus 1 over n plus 1, times another 1 over n plus 1, x to the n plus 1. So I'm going to write it as squared times x to the n plus 1. And that's what calculus books look like. So if you really like that stuff, yeah, that's right, Syro, plus C. If you really like that stuff, you should be a pure mathematician. That's what I went to grad school for. It was really fun. I liked doing that kind of stuff and deriving formulas and proving things. That was my thing. So I've spared you from a lot of proofs this year. I used to make it a lot worse, but that's kind of an interesting one.